Today we're finally going to move away from some set theory and we're going to start talking about binary relations. And so the idea of a binary relation is that it is any abstract way of comparing two elements to each other. And so we can think about binary relations as things that we've seen before, like maybe equals, or less than or equal to, or subset, or divisor of, or any way that we can compare two mathematical objects to each other. And so we're going to start with this abstract definition, but then we'll see a bunch of examples to make it clearer. And so first of all, if we have two sets A and B, then any subset R of the Cartesian product A cross B is called a relation from A to B. And a lot of the time we only care about the situation when A and B are equal to each other, in which case we just call it a relation on A. And so before looking at the rest of this definition, I want to just start immediately by looking at example 1 right down here. And so we care about the relation less than or equal to on the set 1, 2, 3. And so the idea of a relation is that we're just going to write out all of the possible ordered pairs that correspond to being less than or equal to on this set 1, 2, 3. And so in this case, we would write R is equal to the long list of ordered pairs where this is true. And so I want to sort of stay organized when I'm writing out all the possible ordered pairs. And so I'll start by writing the ordered pairs where the first element is the smallest possible. And so that will be 1, comma 1, and then 1, comma 2, and then 1, comma 3. And so all of these are in the set because in every case it's true that 1 is less than or equal to 1, and 1 is less than or equal to 2, and 1 is less than or equal to 3. And so these are all elements of my relation. Now I'm going to do the pairs where it starts with a 2, and so the options here are 2, 2, and 2, 3, because 2 is less than or equal to 2 and 3. And then the last one I'll have in this particular one is the ordered pair 3, comma 3. And so this relation just describes all of the possible less than or equal to possibilities for the set 1, 2, 3. Okay, and so now that we have this, we'll see that going back up to the definition, there's more than one way of writing things in a relation. One of them would be x, r, y. That's shorthand for saying that x comma y is in the relation. And so jumping back down to this first example, we could say either that 1, comma 2 is in the relation less than or equal to, or we could say that 1 is less than or equal to 2. Both of those mean the same thing. So this is certainly an abstract way of looking at the symbol less than or equal to, where now that symbol is a list of ordered pairs, but these both just mean the same thing. It's just notation. Okay, so one thing I want to talk about in terms of representing relationships before we talk about more about categorizing them is that often it helps to draw things graphically. And so one way of drawing the relation would be to draw 3 nodes corresponding to the numbers 1, 2, and 3. And then I can draw arrows between these nodes whenever there's a relation from one of the nodes to the other. And so for example, in this problem, I could have an arrow from 1 to itself because it's less than or equal to itself, and then also from 1 to 2, and from 1 to 3. And then I'd also have an arrow from 2 to itself, and then up to 3, and then another arrow from 3 to itself. And so this is another useful way of representing this relation. Okay, so one of the main reasons that we want to talk about relations is to categorize them so that we can make comparisons between the comparisons that we're making. And so in other words, if I come up with some new way of comparing two mathematical objects, I want to know if that new way is similar to other ways of comparing mathematical objects, so that then I'll have a bunch of tools at my disposal. And so the next 4 bullet points in these definitions all correspond to certain categories of relations that are important in math. And so we're going to want to be able to check whether or not these categories hold or don't for a given relation. And so the first one is reflexive, and a relation is just reflexive as long as everything is related to itself in the relation. And so for this particular example, number 1 again, this is reflexive because 1 is related to itself, 2 is related to itself, and 3 is related to itself. So all the elements are related to themselves, and therefore it is reflexive. In terms of the graph, reflexive would mean that every node has a loop to itself. And so you can see that in my graph, that's definitely true here. Now, a relation would be called symmetric if every time that x is related to y, we also know that y is related to x. And so, in other words, it's symmetric if whenever an ordered pair appears one way, it also appears the other way. And so this relation that we just looked at is not symmetric. And so the reason that it's not symmetric is that 1 is less than or equal to 2, but 2 is not less than or equal to 1. And so that relation doesn't hold both ways. In terms of the graph, what we'd have to have in order for a relation to be symmetric is that every time that there's an arrow one way, that would imply that the arrow would have to be the other way in order for it to be symmetric. And that's not true here. And that's because we can see that there is an arrow from the node 1 up to the node 2, but there's not an arrow from the node 2 to 1, so they don't go both ways. All right, the next one is transitive, and that one always looks a little bit complicated, but I promise it's not that bad. If we have a relation from x to y and a relation from y to z, then transitivity means that we would also have to have a relation from x to z. And so in this example down here with the less than or equal to, this is transitive. And that's because if we know that a is less than or equal to b, and b is less than or equal to c for any numbers a, b, and c, that does imply that a is less than or equal to c. And so in other words, whenever we have that middle value, we can just cut it out and relate the outer two values. That's always valid here, and so it is transitive. Again, I want to be able to think about this graphically. And so if we were to have 3 nodes graphically, then this would mean that every time that we have a little jump between these nodes from A to B and then from B to C, that implies that the direct jump needs to be present in my graph. And so I can check that here in this graph, I do have the jump from 1 to 2 and also the jump from 2 to 3. And you can see that indeed I also have the direct jump from 1 to 3. And so the transitivity condition is met here in this case. One weird thing about transitivity is that A, B, and C are allowed to be duplicates in the definition. That's okay. You'll see some examples later on where that's important. Okay, so the last thing that we care about here is antisymmetry for now. And so antisymmetry does not mean the opposite of symmetry, even though that's what it sounds like. A relation can both be symmetric and antisymmetric at the same time. And so we do have to be a little careful about this definition. But what it says is that every time that x is related to y and y is also related to x, that implies that x must be equal to y. Okay, so now we have to check what that means in this example for less than or equal to here. And so for this particular example, if A is less than or equal to B and B is less than or equal to A, then we do know that that does imply that A would have to be equal to B. There's no way we can have that relationship both ways, and so it is antisymmetric. All right, and then I also want to think about, again, what that means in terms of a graph for a relation. And so that would mean if you have 2 nodes here, then you're never allowed to have something like this, which goes in both directions. And so you would be allowed to have one arrow from a node to the other, but you can't have the opposite arrow if you're talking about 2 distinct nodes. Okay, so I want to look at just a couple more examples of relations to make sure that these definitions are making sense, and then I'll ask you to look at some later. And so the next example is the relation defined by equality on the set 1, 2, 3, 4, 5. And so for this relation, the equals is equal to this long list of ordered pairs, where this time 2 numbers are only related if they are equal to each other. And so that means that the only ordered pairs I'm going to have are the things where the front part and the back part are the same. And so this one is a relatively short relation to write out. It just looks like that. And so this is almost stereotypically the example of a relation that is reflexive, because every single thing is related to itself. That's pretty clear here. It's also symmetric, and that's because if we flip the order of any of these ordered pairs, we end up with the same ordered pair, and so it's still in my relation. This one is trivially transitive because there's no way of moving between distinct nodes anyway. And so every time that we have that A is related to B and B is related to C, already A, B, and C would need to be equal to each other in this example. And so of course A is related to C. And then the last thing here is antisymmetric. And so that means that we would never be allowed to have A is related to B and B related to A whenever A and B are not equal. But it's already never the case that unequal components are related in this example. And so trivially, again, this example is antisymmetric. And so again, I could draw a graph of this relation. And so I'd have the nodes 1, 2, 3, 4, and 5. And all of the nodes would just have arrows to themselves. And so if I check off this list one more time, it's definitely reflexive because every node has an arrow to itself. It's definitely symmetric because this never happens. And so trivially, the other relation, the backwards arrow, is always there whenever the front arrow is there, because the front arrow is never there to begin with. It's also trivially transitive because this sort of thing never happens. And so there's nothing to check. And then also it is antisymmetric, again, because this never happens. All right, so this is a little weird example in terms of looking at the graph, but as you see more examples with graphs, it'll be clearer. Okay, so now let's look at the relation where x is related to y if x squared is equal to y squared on z. Okay, so in order to write out the list of ordered pairs here, I want to think about what possible situations are there where x squared is equal to y squared, and what's the difference between this and x equals y. And you can tell that the difference is that the signs might be different now. And so in this case, we could have, for example, 1 be related to minus 1 because 1 squared and minus 1 squared are the same. And so this relation will be best written out in some bands, where the bands that I write out, everything is related between a band. And so that might not make sense verbally, but when I start writing it, it will. And so first of all, 0 is related to itself, just because 0 squared is 0 squared, and there's nothing else that's going to be related to 0. On the other hand, if I talk about 1, 1 is related to itself, but it's also related to minus 1, and I can write that in both orders because it doesn't matter if I write 1 squared is equal to minus 1 squared or minus 1 squared is equal to 1 squared. Either way, the relation is true. And then I can also write minus 1 comma minus 1. And so the point here is that this band talks about all of the plus minus 1 possibilities. And so, in other words, it's sort of expressing the fact that any combination of 1s and minus 1s between the first and second coordinate are going to be related. So every possibility is on that band. And then we could write the 2 band after that. And so it would look exactly the same as the 1 band, where I'm just having different combinations of plus and minus 2. And then I could do the 3 band, which again would just be 3, 3, 3, minus 3, minus 3, 3, and minus 3, minus 3. And then this would just continue on forever. And I am realizing here that I shouldn't have written z right here at the beginning. I'm sorry, that should have been an r. Okay, so now that we've expressed this, I do want to look at the graph again. And so if I draw the graph of the number line here, then I'm going to have a 0, 1, 2, 3, minus 1, minus 2, minus 3, minus 4. Maybe I'll draw a 4 up here just to be consistent. And then it goes off forever in this number line. And so we could see that this relation is going to look like this, where I have 0 going to itself. And then I have 1 and minus 1 going to each other and themselves. And then I also have 2 and minus 2 going to each other and themselves. And so you could see that I'm sort of getting these concentric rings here for this relation. Okay, and so now if I sort of relate this back to the definitions that we've seen before, it'll turn out that this one is symmetric because the arrows always go both ways. If I have an arrow go one way, it does go the other. It's also reflexive because everything is related to itself. It's also transitive because every time that I take two arrows between nodes, I can find one arrow that goes directly between them. And so in other words, if x squared is equal to y squared and y squared is equal to z squared, then it is the case that x squared is equal to z squared here. But in this case, it's not antisymmetric. And that's just because there are nodes like -2 and 2, where there's an arrow going between them both ways. And so therefore it is not antisymmetric.